In the fall of 1973, the Organization of Arab Petroleum Exporting Countries instituted an oil embargo that quadrupled prices almost overnight. This geopolitical crisis exposed the vulnerability of United States energy infrastructure, transforming fuel efficiency into a vital matter of national security. At the time, the commercial trucking industry operated under a design paradigm that largely ignored the principles of aerodynamic efficiency. Because diesel was inexpensive, manufacturers prioritized maximum cargo volume and maneuverability within regulatory length limits. The result was the heavy-duty cab-over-engine truck, characterized by a blunt, vertical front face and sharp 90-degree corners. Moving these box-shaped objects through the atmosphere creates a physical resistance that is difficult to visualize. A standard tractor-trailer traveling at 55 miles per hour displaces 18 tons of air for every single mile traveled. The flat front of the cab essentially acts as a bulldozer, compressing the air ahead of it and creating a high-pressure stagnation zone. At highway cruising speeds, roughly half of a heavy truck's engine horsepower is expended solely to overcome this aerodynamic drag. The physical manifestation of this resistance became apparent to Edwin Saltzman, an aerospace engineer at NASA's Dryden Flight Research Center. While bicycling to work in 1973, Saltzman felt the tidal wave of high-pressure air from a passing truck push him toward the shoulder, followed immediately by a powerful suction effect from the low-pressure wake pulling him back toward the lane. Saltzman recognized that these passing trucks were expending kinetic energy to violently churn the surrounding atmosphere. Reducing this resistance became a core objective of the federal energy response, authorizing NASA engineers to apply aerospace fluid dynamics to the nation's commercial fleet. This is the standard aerodynamic drag equation. Because drag increases with the square of the velocity, wind resistance becomes the dominant force acting against a heavy vehicle once it reaches highway speeds. To generate empirical data that the freight industry would trust, the Dryden engineers utilized coast-down testing. By accelerating an instrumented truck to highway speeds, disengaging the drivetrain, and measuring the rate of deceleration on a flat surface, they could mathematically isolate the aerodynamic drag from mechanical variables like engine efficiency. The team established a baseline using a retired delivery van covered with flat aluminum sheets to create sharp 90-degree corners on all sides. This configuration, nicknamed the shoebox, exhibited a drag coefficient of 0.52. The engineers began a methodical process of shape modification. By simply rounding the sharp front vertical corners of the aluminum shell, allowing the air to maintain longer attachment, they recorded a 52% drag reduction. To address industry concerns regarding cargo space, researchers calculated the volumetric impact. Rounding the vertical corners reduced drag by nearly half, while decreasing the internal volume by only 1.3%. Sealing the underbody and wheel wells to prevent air from tumbling through exposed chassis components yielded an additional 7% reduction. These elementary modifications proved that significant fuel savings did not require a commercially unacceptable sacrifice of cargo capacity. After refining the shoebox van, Saltzman scaled these principles to a full-size cab-over-engine tractor. By rounding the cab's blunt corners and adding roof fairings, fuel consumption dropped by 20%. These results indicated that aerodynamic efficiency requires integrated whole-vehicle optimization rather than isolated front-end additions. Despite NASA's data, truck manufacturers were constrained by federal laws but limited the combined length of the tractor and trailer. Adding a sloped, aerodynamic nose to a cab meant reducing the length and the profitability of the trailer. A shift occurred with the passage of the Surface Transportation Assistance Act of 1982. This legislation mandated that states permit trailers up to 48 feet in length, effectively decoupling trailer limits from the overall vehicle length. The market shift was immediate. At Peterbilt, the flat-faced cab-over-engine design plummeted from 65% of sales in 1982 to a mere 1% by 2004. With the legal penalty for longer tractors removed, manufacturers adopted the conventional cab design. This provided the necessary space to integrate NASA's recommended sloped hoods, rounded fenders, and roof fairings into standard production models. Advanced testing moved to the National Full-Scale Aerodynamics Complex at NASA Ames. Utilizing wind tunnels large enough to accommodate a complete tractor-trailer, researchers provided the industry with granular metrics on component-level drag reduction. While NASA research defined what was physically possible, federal policy served as the gatekeeper for its widespread adoption across the highway network. While Dryden worked on macrogeometric shaping, NASA Langley explored localized flow control. They focused on vortex generators, small, shaped surfaces protruding from the vehicle body, designed to draw high-energy air down to the surface. These surfaces create controlled, counter-rotating vortices. When applied to the rear of a trailer, these vortices simulate the tapering effect of a physical boat tail, without the solid structure that would impede loading dock operations. Collectively, these aerodynamic evolutions reduced the industry average drag coefficient from 0.80 to 0.65, a 20% improvement. The Department of Energy and Lawrence Livermore National Laboratory estimate that widespread deployment of these devices saves the United States over $10 billion in annual diesel fuel costs. Environmentally, these drag reductions prevent the release of over 36 million tons of carbon dioxide every year. The modern commercial semi-truck stands as a testament to technology transfer. Every side skirt, integrated fairing, and tapered tail traces its lineage to the fluid dynamic expertise developed by the space agency.